Good morning, afternoon, or evening, everyone. My name is Tom Beucler, and I am an assistant project scientist at UC Irvine, affiliated with Columbia University. And today I will share some of our recent progress towards developing physically consistent and data-driven models of convection. I would like to thank Elizabeth Barnes and Emil Ebert Uphoff, as well as the KGML organizing committee for inviting me today, as well as my co-authors listed below. The primary motivation for this talk is that our largest uncertainty in long-term climate projection come from clouds. More specifically, models fail at representing the effects of fine-scale cloud and turbulence on climate because most climate models use a coarse grid with empirical models of clouds, which distorts the multi-scale interaction between climate, convection, and clouds. Fortunately, thanks to computational advances, we are now able to run global simulations with a grid fine enough to explicitly simulate deep cloud systems. However, because of computational limits, we are only able to run such simulations for a short period of time. For example, 1 year, which pales in contrast to the 100-year simulations we need for long-term climate projections. Now, the third motivation is that in parallel to the development of global cloud resolving models, progress in stochastic optimization has improved machine learning algorithms to the point where they can be trained on these high-resolution simulations to then accurately mimic the effect of deep cloud systems on climate. And to make things a little more concrete, I'm going to show you the setup that we typically use in our lab to machine learn subgrid scale thermodynamics for climate modeling. We use a superparameterized community atmosphere model, which combines an exterior coarse model similar to traditional climate models, coupled to two-dimensional cloud resolving models that are embedded within each grid cell. And they produce a more faithful response of clouds, convection, and fine-scale turbulence to the large-scale environment. And so by training a neural network on for example, the first year of these superparameterized simulations, we can unambiguously emulate the mapping from large-scale thermodynamics to how convection and fine-scale turbulence redistribute water vapor and temperature in the vertical. And therefore, we can accelerate the superparameterized model by 2 orders of magnitude, while still keeping the advantages provided by the cloud resolving models in the superparameterized models. And so now visually, what that looks like is that on top, I'm showing you the original superparameterized model, and at the bottom, I'm showing you the neural network emulation. And what you can see is that despite a little bit of loss of the variability, the neural network does a relatively good job at emulating both the convective moistening on the left and the convective heating on the right. Now we are at the very dawn of what we can do with machine learning emulation of climate models, and there are a lot of problems we need to address. And today I'm going to talk about 3 problems. The first problem is that machine learning algorithms typically violate conservation laws. So on the top, I'm showing you the residual from the mass conservation equation, and on the bottom, the residual from the enthalpy conservation equations. I'm going to take several samples from my climate models and run them through the neural networks. If the neural networks perfectly conserved mass and energy, we would have all the samples would have 0 residual from the mass and enthalpy conservation. Instead, if we take a typical neural network, we get a lot of energy and mass violation, up to 100 watts per meter square, just within 1 time step, which is very problematic from a climate modeling perspective, even if the accuracy could be decent. Now, a second problem is that machine learning algorithms typically fail to generalize to out-of-sample climates or out-of-sample atmospheric regimes. So here, I'm taking a daily mean tropical profile from a reference climate, and I'm trying to predict the convective moistening, which is how water vapor is redistributed in the vertical by convection in clouds. In black is the truth, and here are the predictions from different neural networks. In blue are brute force neural networks, and other networks that were engineered to this time conserve mass and energy. They all perform well on the reference climate. However, if I now warm my surface by 4 Kelvin and reevaluate those neural networks in this new climate, what you can see is that they tend to produce very large errors, including the neural networks that were constrained to physically constrained to conserve mass and energy. And this is the second central issue we will address today. The third issue I wanted to talk about arises when we take a step back from the modeling world and look at the current global observing system. So we can currently approximate the large-scale thermodynamics state to a reasonable extent and directly inform the development of climate models. But then the same statement cannot be made for the moistening and heating tendencies from convection that we are interested in if we want to resolve these problematic clouds for climate models. Because these are residual quantities that we cannot directly measure, and so we can only accurately measure them via costly and targeted field campaign, such as the recent Eureka field campaign in the Barbados. And what that implies is that we have to work, if we want to resolve the effect of cloud and convection on the climate, with very sparse and localized data to develop data-driven parameterization of convection. And this is challenging. So these three problems lead to the central question of my talk today, which is directly in line with the workshop's goal. How can we design models of convection that are both physically consistent and data-driven, including cases where data is sparse? And my talk will have 3 parts. First, I will compare 2 methods to enforce conservation laws in neural networks and introduce the notion of architecture and loss-constrained neural networks. Second, I will show how physical rescaling can help neural network generalize and introduce the notion of climate invariant neural network. And finally, I will show that these climate invariant neural networks learn more general mapping from climate to convection with very little data, with the potential of facilitating transfer learning between idealized and realistic atmospheric data. And finally, note that while I am investigating the specific case that can seem quite specific of subgrid scale thermodynamics deep learning parameterization for climate modeling, the framework that I'm going to show today has ideas that are general enough to be applied to machine learning emulation of physical models, for example, but not limited to meteorological and oceanic models. So coming back to the first problem motivating this talk, we ask, how can we enforce physical constraints in data-driven models of convection? In our case, we'll propose solutions applied to the conservation of mass, energy, and radiation in neural networks. And we use neural networks in our case because they have high representation power and scalability. But some of these ideas could be transferred to other machine learning algorithms. So the first step is to add all the terms informing conservation laws to the neural network's inputs or outputs. And once you do that, I'm going to present 2 options to enforce conservation laws in neural networks. The first option has already been covered in this workshop, is to introduce soft constraints in the loss function by introducing a penalty for violating conservation, which in essence is similar to a Lagrange multiplier. So the loss function is in the sum of a performance loss, for example, mean squared error, and then a weighted term that represents how much the neural network violates conservation law, for example, the squared residual from the conservation laws I showed you earlier. And then the second option I'm going to introduce today is how to enforce hard constraints by changing the architecture of the neural network. And more specifically, I'm going to introduce a general method we developed to enforce conservation's law to within machine precisions, which I'm showing below. So we start with a standard neural network, mapping inputs x to an output vector y of total length p. But if we have n constraints that we exactly know in this case, instead of directly outputting p components, we only output p minus n components. And then we calculate the remaining components using fixed constraints layers that encode the conservation laws. And then by concatenating both these direct and residual outputs, we can optimize the neural networks using the whole output vector, which means that the loss function gradients can propagate through the constraints layers, which means that the constraints in the end inform the final weights and biases of the standard neural network that we optimized. So now on to the results. I'm going to first show you the mean squared error of the two different options I presented, and show you that when we use loss constraint networks, there is a trade-off between performance of the network and physical constraints of the network. So on the y-axis is a mean squared error representative of the skill of the neural network. We start with an unconstrained network where we haven't enforced any constraints. Up is bad, down is good. First, if we look at a multiple linear regression, we should always start with simple examples. We can see that we do significantly better than a linear regression, as the y-axis uses a log scale, which is reassuring. It was useful to use a neural network to begin with. However, once we look at the squared residual from the conservation law, which is the energy or the mass leak, what we see is that the neural network, the typical neural network, violate conservation law so much that it does worse than a linear regression. And then as we enforce conservation with more and more weights in the loss function, we can see that the neural network follows conservation laws more and more closely, while it performs worse and worse. So there is a trade-off here. While if we enforce conservation's law in the architectures of the neural network, the constraints are enforced within machine precision and we get competitive performance, which we're quite happy about. Now I'm going to transition to the second problem, which is that even when you physically constrain the networks, they still fail to generalize, as I showed in the motivation of this talk. And the idea was that we had is to first break the model even more to better understand our failure case. And so we're going to introduce a very provocative generalization experiment where we train and validate our models on a cold aquaplanet simulation and then test the models in the deep tropics of a warm climate that has a surface that's 8 Kelvin warmer than the cold climate. So from the perspective of the surface temperature, here's the cold climate, here's the warm climate, here's the deep tropics where the warm climate has surface temperatures that the neural network would have never seen if it was trained on the cold climate. And so we train the neural network on a cold climate and we test it out of sample in the tropics of the warm climate in purpose to break it as much as we can to better understand how it works. So taking a daily mean tropical prediction in the cold climate, the first condition is to check that a neural network is a good fit. So it is a decent fit in the cold reference climate. And now we look at the deep tropics of a warm climate. It's now 8 Kelvin warmer and it fails even more miserably. And our goal is going to be to help the network, give it physical information so that it can generalize better to this warm climate. And so the framework that I'm showing today is based on physical rescaling of the data so as to convert what is an extrapolation problem into an interpolation problem. And so the brute force network is not climate invariant in the sense that you cannot use the same mapping from the cold climate and the warm climate since it breaks. And we want to physically rescale this variable so as to make it climate invariant. And we're going to ask how to choose that physical rescaling. Note that it's not a well-defined problem because there could be several physical rescalings that work. And today I'm going to show a physical rescaling that gives us promising results, and that is based on the main mode of failure of a neural network, coming from the Clausius-Clapeyron relation, which implies an exponential relationship between water vapor and surface temperature. And this is a striking nonlinearity, which is the main cause in our case of the failure of a neural network, as it is hard to extrapolate without knowing that upper bound dictated by physics. If you just look at the blue curve, the cold climate, the neural network could very well predict the warm climate to go in this direction with the orange arrow, or this direction, and both of them would be correct from the cold data in a sense, but would lead to significant errors in the warm climate. And so the idea is to use that upper bound to better extrapolate to a warm climate. And just for the interest of time, I'm going to skip over some of the algorithm and just give you one example, which is that if we rescale the specific humidity, which is an input of a neural network model of convection, to relative humidity, which tends to be more climate invariant. As you can see, it has more similar probability distribution functions. We can go from what seems to be an extrapolation problem to an interpolation problem and dramatically improve our generalization results. Now, I overestimated my time a little bit here, so I'm going to skip just to get to the interesting part, to the last part of my talk. You can replay this game for temperature and latent heat flux, and the resulting climate invariant neural networks generalize better to unseen climate. You can get to a reasonable performance in a warm climate, even if it was never trained on it, and it's really far surface temperature-wise. The last result that I wanted to share is that, and I think the next speaker can speak more about it, is that if once you physically rescale those neural networks and then use them to do transfer learning from idealized aquaplanet data to real geography data, which is quite analogous to a problem we have to an idea a lot of climate scientists already have, which is to train the neural network to extract all this rich information we have from climate models and then fine tune it using observations to produce more realistic model. We can recreate that idea, and we have a numerical laboratory for that idea where we oscillate between aquaplanet, ocean world simulation, and real geography simulation. What we can see is that as we transfer from an ocean world to a real geography world, and look at the performance of the climate models on the y-axis, with no data, even with no data, the climate invariant neural network is significantly better at guessing the different regimes. So even if it has only ever seen an ocean world, it performs much better on a real geography planet than a brute force neural network. And it also tends to learn more with less data, less sample trained on. And these are exciting preliminary results that confirm that climate invariant networks, maybe like physical rescalings, could be a way forward to improve the generalization properties of neural networks from the climate we live in, and we can take observations of from that climate to a future climate that we don't yet have observations from. So I'm just going to skip to the conclusion, is that we can make neural network models of convection physically consistent by enforcing physical constraints, either approximately in the loss function or exactly by modifying their architecture, and that we can help neural networks generalizing by physically rescaling inputs and outputs. And I want to note that those are two different methods of incorporating, taking a step back and going back to the workshop's themes. These are two different ways of incorporating physical knowledge in neural networks. So the forward arrow described by Elizabeth Barnes for different purposes. Finally, we also find that climate invariant neural networks learn more general mappings and facilitated transfer learning, which is an excited, and one aspect I find particularly exciting about that is that what it means is that physics-guided machine learning may be one of our most promising tools to assimilate sparse observational data from observational field campaigns into global climate models in a way that's physically consistent. And with that, thank you all for attending, and below is a link to my website where I share preprints, code, and resources related to my research. Thank you again, and I'll, yeah.
Thank you, Tom. So we have some questions here. We only have time for one question right now, and we'll take the rest of the panel. So one question came in is, which other applications do you think your methods would apply to? Anything in mind, any low-hanging fruits?
So our application is to replace existing empirical parameterizations convection in climate models, which are the main sources of uncertainty for long-term climate projection, with machine learning parameterizations. And those are two ways of making those machine learning parameterizations, which are probably which are going to appear more and more, I'm expecting in the community, more robust. Which means they will produce less generalization errors and will have better control over how much mass and energy they leak. But then other applications are any system where you have a strong physical prior of how you change from, for example, regime A to regime B, but you only have data from regime A, and you also want to predict regime B. And I think that's relatively general.
All right, thank you.